All right, this is 9.3, which details Taylor series. So we just covered Taylor polynomials, right? Which is just a pretty quick recap. A Taylor polynomial basically approximates a function, right? Because this is equal to something to the n, right? When we start at k, and we define this as this, right? Assuming this is centered at a, and x minus a to the k, right? Is some series, some sequence, or some sum of, it's some sum of polynomials, right? But notice how this n, right, kind of is a problem in making this a good approximation. And we showed earlier that we can set the remainder as something, right? We can even have f at x is equal to Pn of x plus Rn of x. So clearly, solving these Taylor polynomials are a pretty big, we gotta figure out how to do that, right? And so what we arise at is taking the limit as n goes to infinity of one of these limits. Because essentially, what we do here is we get an infinite sum of a function that theoretically should be the exact same as the function we're looking at, right? Now, this isn't always the case, and I'll illustrate some cases of why. But before we do this just a heads up. This chapter is extremely similar to just Taylor polynomials, right? Except now we have an infinite sum. But it isn't until we get to the applications when I guess it becomes more interesting, and I don't really know how to call it, but yeah, I mean, there's not much in the chapter, honestly. There's a few theorems that I think are kind of nothing burgers when it comes to what we have to know in the course. But there is an interesting case study in here. There's they present theorems that I kind of feel like kind of nothing burgers. Like they don't really use it to apply to anything. So I'm gonna assume it's just there for just so you know. And I probably won't cover it too much in detail. I might just mention it. But anyway, let's do the first activity, right? And I'll also try to connect this back to remainder theorems whenever I can, especially when we get to analytic functions. Okay, so the first thing we're going to try to do is determine the Taylor series and interval convergence for f at x is equal to x squared times e to the negative x squared. See if you can solve this. And for this is what we have to do. E to the negative x squared. We know the Taylor series for e to the x is given by the infinite sum of x to the k over k factorial, yeah? Oh yeah, by the way, this is centered at 0. Okay, so plugging in negative x squared, and this is for all real numbers, by the way, right? The interval convergence for this is all real numbers. And these are just our Maclaurin series, right? These ones you should have, I don't know if they expect us to memorize it. I think they do, so memorize them. But we can see at negative x squared, right? And now the domain is still the real numbers, right? Because negative x squared is a subset of the real numbers, right? So then this is equal to negative x, a to negative x squared, right? And now we can just plug that baby in. And then we can expand out. And now we can plug them right back in. Now we can write f at x is equal to x squared times e to the negative x squared, which we can represent like this, right? So we'll just place him right in there. And now we can multiply in x squared, just like normal. So these behave just like Taylor polynomials, except now we don't have n, we have infinity. And I'm pretty sure we denote Taylor series with like s and x, or something. I'm not too sure. They don't really mention that. But yeah, that's the answer. And now you want to figure out the interval of convergence, right? And doing this, we can just do a ratio test. Good old ratio test. K goes to infinity. In fact, I'm going to do the test where you start with the kth term over the k plus 1 term, and that'll directly get you the radius of convergence. So I'm going to do this. These are all absolute valued. Cancel k plus 1. And this goes infinity, meaning the radius is infinity. Meaning this is true for all real numbers. It's convergent for all real numbers. And boom, we got it. There's our answer. Our interval of convergence is the real numbers, and this is our Taylor series of f at x. All right, sounds good. Now for our second example, it's a bit more tricky. So I'll run you through the logic, or if you want to try on your own, that's also fine. Let's try to find the Taylor series and radius of convergence for f at x is equal to sin of x. This is the harder part, a is equal to pi over 4. All right, now before we do anything, we have to see exactly how we're going to do this, because it's very easy to just rush into this, be like, oh my god, let's do it. Let's just have the Taylor series, the Maclaurin series for sin, right? So this is -1 k 2 x to the 2k plus 1 over 2k plus 1 factorial, and I guess we'll just shift it to the left. But no, you'd be wrong. Even if you have like x minus pi over 4. No, you'd be wrong. I'll now explain why. What this details is the Taylor polynomial centered at 0, evaluated at pi over 4. So it's actually not the Taylor series centered at a equals pi over 4. I'm pretty sure it doesn't end up making a difference for the Taylor series, because sin x is analytic, I think, meaning it's the same. But what we're meant to do is, let's write down the form of the Taylor series. Actually, we can ignore this limit. We can just write straight up, just. And the form of the Taylor series is f prime of k. And instead of 0, which is how we derived our Maclaurin series before, we have pi over 4. And then we have x minus pi over 4 to the k. And now we can take a look at something. We can see we have sin of pi over 4, right? And sin of pi over 4, this is 1 over root 2, right? If we draw our cast grid, right? 1, 1, root 2, right? And that's the same with cos. But then we have negative sin is obviously negative. And same with negative cos. And notice how this goes through all of the possible derivatives of sin x. Right? Zeroth derivative, first derivative, second derivative, third derivative, right? And then we cycle back to sin. So when we have our k and our f to the k, right? Notice that when k 0, 1, 2, 3, 4, right, we get 1 over root 2, 1 over root 2, negative 1 over root 2, negative 1 over root 2, and 1 over root 2, and the cycle continues. So you could try to find a function that oscillates between negative 1 and 1 every, like, where it goes one positive, positive, negative, negative, positive, positive, negative, negative. But the easier thing to do is just to separate it into two series, because this is positive, this is negative, this is positive, and then the next even term is negative. And same with the odd terms. The odd terms, we can go positive, negative, right? So we should just split this up into two sums. And let's just do that. We know also that the derivative will be 1 over root 2, right? And then let's have our first one. Our first one's is for all even. Let's say even. So we should have 2k, right? 2k will give us all even terms. So let's have negative 1 to the k, because that just oscillates each time, right? And then we'll have x minus pi over 4 to 2k. And we'll have 2k factorial. Okay, and we'll add our next term as well. And this one should be even, right? Oh, sorry, odd. This one should be odd, right? And notice how this will get us every single term here. And then this one gets us every single term here. And so when we add the two together, we end up with our entire series. The reason why this is nice to do instead of Taylor polynomials is because this is to infinity, right? With Taylor polynomials, we might have had to be more careful. It's like, oh my god, we can only go up to like n over 2 before, or else we'll get too many terms, right? With infinite sums, we don't really care, right? So for this one, we'll factor out the 1 over 2, and we'll end up with two Taylor series that look oddly familiar. Well, negative 1 to the k. Over 2k factorial. And we have x minus pi over 4, 2k. And what do we see here? Well, this is our cos, right? And this looks like sine, right? When we talk about the Maclaurin series. But we have this minus pi over 4. What this means, okay, is that this is equivalent to saying cos evaluated at x minus pi over 4. See that? Because our Maclaurin series for cos x is equal to this. Oh, sorry. So when we add a x minus pi over 4, we're basically saying, okay, so take that same Taylor polynomial, right? That might look like something like this, right? And evaluate it at x equals x equals pi over 4. That's what we're doing. And the same with this one's sine, right? And we see that this is our answer. You can simplify this further, but you don't have to. Boom, that's the answer. And we also know this is the case on the real numbers, right? Because there's no term in here that, like here, that is not true outside the real numbers. All of these have interval of convergence real numbers, right? So the final one should also have real number convergence. Great. The question didn't really ask for interval convergence though, so it's fine. Now I want to investigate when a Taylor series isn't actually equal to its function. Because right now you might be thinking, oh, okay, yeah, every single Taylor series is just the function. That's great. Well, not exactly. And I'll give you a nice counterexample. We'll take this piecewise function that is 1 over e to the 1 over x squared when x is greater than 0. And then 0 everywhere else, including at 0. And what I want to show you, that the Taylor series for this function, okay, center at 0. Let's say center at 0. This would be f prime of k at 0 over k factorial times x to the k. I want to tell you that this never equals the function, like really at all. And I'll show you why. If we sketch this function, okay, obviously 0 on this side is just 0, right? And we agree that slope over here is all 0. I want to show you that when we evaluate the slope at 0, we always get 0. Because I'll show you what 1 over e, like I would do the algebra, but I think it'd be cooler to show you negative 1 over x. This is what e to the negative 1 over x looks like. Would you agree that that slope, f prime of 0 is 0? Where's the apostrophe? That's a comma. F prime. Or sorry, maybe not at 0, but because a 0 is a point. But would you agree that around 0, it's a flat line, right? Like it asymptotes towards 0, the slope. So if we take a very small number, right? Notice how it's 0. Decimals breaks down. It's not actually 0. It's very close to 0. And notice how if we were to graph f prime of x, that's also the case. And we can keep on adding primes, right? It doesn't matter. It's always... Oh, okay. Okay, you have to believe me. Desmos just breaks down. It's still there, I swear. Basically, my point is, as we approach 0 on this point, the derivative of this and all of its derivatives also approach 0. And so what we see is that if, the right side and the left side of 0 agree when it comes to what derivative they think is right, then that's the derivative of that point. And we saw that's equal to 0. Which is just equal to 0. Meaning our Taylor series for this function is just a 0 function. But we know that e to the negative 1 over x squared it's a pretty cool function. He's got some personality to him, right? He's a bit more interesting than just 0. So what I'm trying to show to you is that not every function can be represented with the Taylor series and be accurate. And we have a name for the ones that are accurate. We say they're analytical. Oh, sorry, analytic. And this should be familiar with this from Alfonso. It's where for some interval, like arbitrarily small interval, if I'll just write out the formal definition. F is analytic when on I is a delta greater than 0. This is just saying there's some interval. Okay, this is a statement for analytic. And there's another way to check for analytic, and that's with our remainder theorems. If we can see that the limit as n goes infinity of Rn of x over x minus a to the n equals 0, then we've also proven is analytic. And we know Rn of x is equal to whatever the remainder theorem said, which was something crazy. It was fn plus 1 of whatever that guy is over, what was it, n plus 1 factorial times x minus a to the n plus 1, right? And xi is between x and a. So when we plug that guy in, right, we'll actually end up with this. Where we have x minus a and n plus 1 factorial, right? And when we evaluate this, we can evaluate this. So let's do a quick proof of why e to the x is analytic. And we can do it with this. We know the derivative, the kth derivative of e to the x is always just e to the x. Right, so we can rewrite this limit as e to the xi times x minus a over n plus 1 factorial. All right, and now something that people might think is, all right, let's just take out this e to the xi. But the thing is, xi depends upon whatever, depends on n. Okay? Because it depends on Rn. Like, yes, it's between x and a, right? But it depends on Rn, so we don't exactly know. But that's okay because, like we said, xi is between these two numbers. If we can show that it's bounded and those bounds go to 0, then we've proven the inner bound goes to 0. And I'll illustrate this like so. We know exi times x minus a over n plus 1 factorial has to be less than or equal to e to the x times x minus a n plus 1 factorial. And this has to be greater or equal to e to the a times x minus a over n plus 1 factorial. This is the case when a is less than x. Okay. And now this limit goes to 0, right? Because x is just a fixed constant. This goes to 0 because a and x are just a fixed constant. Meaning this inner function must also go to 0. And boom, so that's case 1. And then case 2, when x is less than a, we have the exact same argument, literally the exact same argument. Yeah, like, well, we can literally just copy and paste this guy. Just my god, please let me copy. Like we can just have this guy, except here we evaluate at a and here at x. This goes to 0. This goes to 0 as n goes to infinity. Right? So this guy also goes to 0. And boom, we just proved it analytic because we proved that this remainder goes to 0. I think you can even just do, if you just prove the remainder itself goes to 0, that's also enough. So, you know, I feel like this just makes it kind of, like, yeah. Because otherwise you would have n plus 1 here, which I guess you could still do. But anyway, that's how you show a function is analytic. All right, let's move on. And yeah, with Taylor series, we can also do integration, derivation, the same way we did with polynomials and power series. So in fact, Taylor series are actually not a big jump from just combining Taylor polynomials and power series. Let's take a look at this function. Let's find the Taylor series of f at x is equal to, here we go again, arctan of x. He's back. And let's also find his interval of convergence as well. So, try on your own, but here's how you do it. We have f at x. And then we derive him once to get 1 over 1 plus x squared. Same as saying 1 minus negative x squared, right? And we know our geometric series, right? And when we evaluate this geometric series and this is true for all x less than 1, okay? And when we plug in this negative x squared, right, we end up with our antiderivative, of our derivative. And then subbing them in, we get negative 1 to the k times x to the 2k, right? And so once we integrate this guy, so we know f prime of x is equal to this guy now. Sorry, I'm switching around n and k, like there's no end in the world, but you know, when we integrate this guy, we'll end up with f at x plus c is equal to this, and then we integrate this guy, right? So this ends up being like this, 2n plus 1. And then when we evaluate at c, f at x is just arctan, right? When we find c, we just plug in x equals 0. So arctan becomes 0, this becomes 0, so c is 0, right? So we can just say arctan of x is represented by this Taylor series. Great. And now for its interval convergence. We can do this in two ways. We can either see that we just use the geometric series and negative x squared. The absolute value of this being less than 1 is the same thing as saying x is less than 1. Okay, so we know the radius convergence is 1. Or if we want to play it safer, we can use ratio test. So we have negative 1, 2n plus 1, n plus 1. And here we have 2n plus 3. Right, and then we have 2n plus 1 over negative 1 to the n. Right, these guys cancel out because of the absolute values. Right, and this ends up just being, it has to, and then we also have, sorry, I forgot the x in here. That's my bad. I'll just put the x's over here. We have x to the 2n plus 3 and x to the 2n plus 1. So we get, these guys cancel out to 1 as well. Right, so we just get x squared less than 1 is the same as saying x is less than 1. And now we should evaluate at the actual points, endpoints. Let's say x is equal to 1. then our series looks something like this. And by alternating series test, this is convergent, right? This guy is positive, decreasing, and approaches 0. This guy's -1, right? And then when x is equal to -1, we see we have this. But then we have, these guys cancel out, right? So then we have this. And in fact, this is divergent. Yeah, because this is comparable to the integral, improper integral, of 1 over 2x plus 1, right? Which we can see behaves similarly, which is equal to ln of 2x plus 1 over 2 between 1 and b, as b goes to infinity. And as b goes to infinity, we end up with like 2b plus 1 over 2 minus ln 3 over 2. As b goes to infinity, this guy goes to infinity, and so it's divergent. So this is divergent by integral test. Yeah? So then our interval of convergence is this. Boom. So that's how we do it. But yeah, that's 9.3. Pretty short one, all things considered. Yeah, no, I'll do 9.4 later. But I mean, it's all pretty. To be fair, this all just builds off the power series and Taylor polynomials, so this is pretty good. And then we'll get into applications later, and then that'll wrap up the unit. It's actually not terribly difficult in my opinion. Actually, this is actually like, it looked a lot harder. I'm guessing the applications are going to be a bit more computation heavy. That's fine. There's actually not that much theory behind Taylor polynomials aside from like remainder theorems. But yeah, there you go. That's 9.3 Taylor series.